Hello guys, my name is EJ and I am an astronomy student from Rizal Technological University in Mandaluyong City. My report is about the gas giant Jupiter. With its mass more than twice the combination of the mass of all planets in the solar system, Jupiter is the largest planet in our solar system. Jupiter's formation took place 4.5 billion years ago, taking most of the mass left over after the formation of the Sun, then settled into its current position in the outer solar system, where it is the fifth planet from the Sun. Jupiter is 11 times wider than of Earth, with a radius of 43,440.7 miles, or 69,991 kilometers. Jupiter has 2.4 times of gravity than of Earth, so if you're on a diet, this would be a stressful place for you to visit. It is located 5.2 astronomical units away from the Sun, where 1 astronomical unit is the distance from the Sun to Earth. With this distance, it will take 43 minutes for sunlight to travel from the Sun to Jupiter. Jupiter takes 4,333 8 days or around 12 years to orbit around the Sun. Though it is the largest planet in the solar system, it only takes 9 hours and 55 minutes for Jupiter to turn around its axis, which makes it the fastest planet on our solar system. Jupiter's equator is tilted with respect to its orbital path around the Sun by just 3 degrees. This means Jupiter spins nearly upright and does not have seasons as extreme as other planets do. The composition of Jupiter is similar to that of the Sun, mostly hydrogen and helium. As a gas giant, Jupiter doesn't have a true surface. The planet is mostly swirling gases and liquids. While a spacecraft would have nowhere to land on Jupiter, it wouldn't be able to fly through unscathed either. The extreme pressures and temperatures deep inside the planet crash, melt, and vaporize spacecraft trying to fly into the planet. Deep in the atmosphere, pressure and temperature increases. Compressing the hydrogen gas into liquid, this gives Jupiter the largest ocean in the solar system, an ocean made of hydrogen instead of water. Scientists think that at depths perhaps halfway to the planet's center, the pressure becomes so great that electrons are squeezed off the hydrogen atoms, making the liquid electrically conducting like metal. Jupiter's fast rotation is thought to drive electrical currents in this region, generating the planet's powerful magnetic field. It is still unclear if deeper down, Jupiter has a central core of solid material, or if it may be a thick, super hot, and dense soup. It could be up to 90,032 degrees Fahrenheit or up to 50 degrees Celsius down there, made mostly of iron and silicate minerals. The global energy budget of Jupiter has been the subject of intensive study and measurement ever since its excess of infrared emission over its net solar irradiance was discovered. Schematic flow of energy within Jupiter's irradiated troposphere and stratosphere, as determined from a combination of Voyager and Cassini measurements and Nemesis model calculations. Solar radiative fluxes are shown on the left in blue, and infrared fluxes on the right in pink. The upwelling interior convective fluxes are in the center in orange. The horizontal dashed line represents the approximate boundary in the atmosphere below which solar insolation does not penetrate. This shows the overall flow of energy within and through the radiative absorption zone of Jupiter. At the top of this atmospheric zone, 12.7 watts per meter squared of visible and UV solar radiation is incident upon the stratosphere and upper troposphere at Jupiter's distance from the Sun of 5 astronomical units, of which around a third is scattered back into space through Rayleigh scattering, stratospheric haze particles, and from the upper cloud layers. Thus, a net total of around 8.4 watts per meter squared or 66 IPU of the incident solar irradiance is absorbed within the stratosphere and the upper troposphere. This combines with the upwelling interior heat to provide around 14.1 watts per meter squared of heat input within the radiative absorption zone, which must therefore be re-radiated out to space in equilibrium. By this means, Jupiter appears to radiate around 111 IPU or 68% more energy in the infrared to space than its net input of solar energy. This style of energy budget is likely to be typical of a whole class of giant planet, in which radiative energy from the parent star combines with the internal heat to produce a dynamically active upper troposphere and stratosphere. The appearance of Jupiter is due to the chaotic spinning interior gases and liquids creating an artistic colorful cloud bands, including his iconic red spot. This great red spot is a gigantic storm, an anticyclone. Just like a hurricane on Earth, the center is relatively calm, but further out, the winds scream at 430 to 680 kilometers per hour. And since there's no solid surface to slow it down, it has been recorded to be enraged for over 300 years. However, scientists has discovered some changes on this red spot. The color is changing and appear to be shrinking and getting rounder. But as more data was gathered, it was confirmed to be actually getting taller. That is why, in our perspective, the spot appears to be smaller and rounder. This great red spot used to have enough size to fit 3 Earths. But after these changes, its size is only a little over Earth. Magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Jupiter is a gaseous planet. There is no magnetized crust that obscures our view of the dynamo deep below, unlike Earth where we can't see all the crustal magnetization that is right beneath our feet. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the Sun, extends all the way out to the orbit of Saturn, and in all likelihood beyond. It's a very large feature in our solar system. Jupiter doesn't only have great red spot, but it also have great blue spot. This great blue spot is an invisible to the visible wavelengths our eyes can see, where the largest changes in Jupiter's magnetic field occurs. With the Juno mission, scientists has confirmed that there is in fact an internal magnetic field in Jupiter that is constantly changing over time, which is called secular variation, likely driven by the planet's deep atmospheric winds. This region is near the equator, where some of the strongest zonal winds of the planet exist. It actually appears that Almost all of the change in Jupiter's magnetic field are coming from this great blue spot. Just like the rest of the Jovian planets, Jupiter also has its rings. Though, unlike Saturn's bright and brilliant rings that's made of ice, Jupiter's ring is composed mostly of dust which don't reflect sunlight. These rings can only be seen in Earth's largest telescopes and will light up when observed in infrared. The rings extend to a distance of 140,000 miles. There are four sets of rings. The outer part are called gossamer rings, which contains the remnants of the moons Thebe and Amalthea, the main ring, and the halo ring. Thebe and Amalthea were heavily bombarded with impacts which flings the moon's materials into space, and the residual dust spread out to form the ring. This ring of Jupiter weighs at least 2.2 trillion pounds. On Earth, the northern lights are caused by solar storms hitting the planet's magnetic field lines. But Jupiter is powerful enough to create its own, as its gravity pulls charged particles inwards, creating aurora 100 of times more energetic than the one we see on Earth. And greatest contributor in creation of this magnificent aurora is its moons, especially Io. Jupiter has 79 known satellites. In 1610, Galileo pointed his telescope at Jupiter and witnessed 3 objects. A week later, he saw a 4th one. Those 4 moons are now called the Galilean moons in his honor. There are other moons that has been discovered recently. But first, let us discuss about Io. Io is a chaotic violent moon, third largest moon of Jupiter and the 4th largest moon in the solar system, with a diameter of 3,643 kilometers. Io is composed of silicate rock, making it much more similar in composition to the rocky planets than the moons. This composition makes it the densest moon in the solar system. Its crust is about 50 kilometers thick and is tormented by massive lakes of molten silicate lava on the surface. Io is extremely geologically active, but despite this constant emission of heat, the moon remains cold. Io has an average temperature of 110 Kelvin due to its distance from the sun. Io's atmosphere is a very thin layer of sulfur dioxide as a result of the volcanic activity, with traces of sulfur monoxide, sodium chloride, and an atomic level sulfur and oxygen. Io orbits Jupiter quickly once every 42.5 hours, which is also the same amount of time it takes the Moon to complete one full rotation, since it is tidally locked like many other moons. This moon around the gas giant is also the subject of a tug-of-war match between Io's neighbors and its parent. Io is locked into what's known as an orbital resonance with its neighboring moons Europa and Ganymede, like a planetary clockwork. Io completes 2 full orbits of Jupiter for every one of Europa and 4 full orbits for every one of Ganymede. This means that every few orbits the moons align, and the gravity of Io's neighbors pulls it out of its circular orbital alignment and into an elliptical orbit, which means that the strength of Jupiter's gravitational influence on the moon is constantly changing, pulling the moon's interior and squashing it. This causes tidal heating. The change in gravity of Jupiter, Europa, and Ganymede causes friction on Io's interior, which generates heat, raising the temperature of Io's mantle to over 1,000 degrees, which would usually be frozen. This heat melts the mantle near the surface, causing geological activity that is responsible for the many mountains, volcanoes, and lava lakes on the surface. As Io travels along this elliptical orbit, Io cuts across the powerful magnetic lines of Jupiter's magnetic field, meaning Io is a hive of electrical activity and radiation. The moon can create an electric current of over 3 million amps, and this causes lightning in Jupiter's upper atmosphere. When the moon passes close by the planet as the moon moves through these massive channels of radiation, these magnetic field lines rip across the surface like electromagnetic tornadoes, and the irradiation from the gas giant strips off approximately a ton of material every single second. This displaced debris becomes ionized by the magnetic field and forms a cloud around Io, which feeds into a much larger rotating cloud of extreme radiation around Jupiter, known as plasma torus. The ions in this cloud have inflated Jupiter's magnetosphere to over twice the size we would expect, thanks to the extra matter from Io. As the planet and the Taurus rotate, some of these ions fall into Jupiter's upper atmosphere, creating brilliant and fascinating aurora.
Ganymede orbits Jupiter at about 665,000 miles. It takes Ganymede about 7 Earth days to orbit Jupiter. Its mean radius is 1,635 miles. Although Ganymede is larger than Mercury, it only has half its mass since it has a very low density. The daytime temperature on the surface averages at minus 171 degrees Fahrenheit to minus 297 Fahrenheit, and night temperatures drop to minus 315 Fahrenheit. Similar to Europa, Ganymede has a tenuous oxygen atmosphere whose formation involves water ice on the surface being split into hydrogen and oxygen through interaction with UV radiation, the hydrogen being lost into space and the oxygen being retained. The surface pressure of this atmosphere is thought to lie within the range of 0.2 to 1.2 micropascals. The presence of this atmosphere also causes an air glow effect, a faint emission of light caused by the interaction of atomic oxygen and energetic particles. This effect is not uniformly distributed, but instead causes bright spots to appear above the polar regions, which could be polar auroras due to the planet's magnetic field. Additional evidence of oxygen atmosphere comes from the detection of various gases trapped in the ice of Ganymede. This evidence consisted of the spectroscopic detection of ozone, as well as absorption features that indicated the presence of oxygen gas. Another constituent of the atmosphere is hydrogen, which, despite most being lost in space, still exists at a surface in very minor concentrations. The existence of this neutral atmosphere implies that an ionosphere should exist since oxygen molecules are ionized by the impacts of the energetic electrons coming from the magnetosphere and by solar electromagnetic UV radiation. However, the existence of an ionosphere remains controversial due to conflicting data gathered by different missions. Ganymede is the only satellite in the solar system to have a magnetosphere. Typically found in planets including Earth and Jupiter, a magnetosphere is a comet-shaped region in which charged particles are trapped or deflected. Ganymede's magnetosphere is entirely embedded within the magnetosphere of Jupiter. Ganymede has a core of metallic iron, which is followed by a layer of rock that is topped off by a crust of mostly ice that is very thick. There are also a number of bumps on Ganymede's surface, which may be rock formations. It is believed that Ganymede has a saltwater ocean below its surface. In 2015, a study by Hubble Space Telescope looked at Ganymede's auroras and how they change between Ganymede's and Jupiter's magnetic fields. The rocking seen by the auroras gives evidence that the probable ocean underneath is salty, more salty than the oceans of Earth. Jupiter's moon Europa. On average, Europa's distance from the Sun is about 485 million miles. Europa is Jupiter's sixth satellite. Its orbital distance from Jupiter is 414 miles. It takes Europa 3.5 Earth days to orbit Jupiter. Europa is tidally locked, so the same side faces Jupiter at all times. Europa is 1,900 miles in diameter, making it smaller than Earth's moon, but larger than Pluto. It is the smallest of the Galilean moons. Jupiter's equator is tilted with respect to Jupiter's orbital path around the Sun by only 3 degrees. This means Jupiter spins nearly upright so that the planet, as well as Europa and Jupiter's other dozens of moons, do not have season as extreme as other planets do. Because Europa's orbit is elliptical, its distance from Jupiter varies, and the moon's near side feels Jupiter's gravity more strongly than its far side. The magnitude of this difference changes as Europa orbits, creating tides that stretch and relax the moon's surface. Like our planet, Europa is thought to have an iron core, a rocky mantle, and an ocean of salty water. Unlike Earth, however, Europa's ocean lies below a shell of ice probably 10 to 15 miles thick and has an estimated depth of 40 to 100 miles. While evidence for an internal ocean is strong, its presence awaits confirmation by future mission. Europa's water surface is crisscrossed by long linear fractures. Along Europa's many fractures and in splotchy patterns across its surface is a reddish-brown material whose composition is not known for certain, but likely contains salts and sulfur compounds that have been mixed with water ice and modified by radiation. This surface composition may hold clues to the moon's potential as a habitable world. Europa has only a tenuous atmosphere of oxygen. However, in 2013, NASA announced that researchers using the Hubble Space Telescope found evidence that Europa might be actively venting water into space. This would mean that the moon is geologically active in the present day. If confirmed by follow-up observations, the plumes of water could be studied by future spacecraft, similar to how Cassini sampled the plume of Saturn's moon Enceladus. One of the most important measurements made by the Galileo mission showed how Jupiter's magnetic field was disrupted in the space around Europa. The measurement strongly implied that a special type of magnetic field is being created within Europa by a deep layer of some electrically conductive fluid beneath the surface. Based on Europa's icy composition, scientists think the most likely material to create this magnetic signature is a global ocean of salty water. And this magnetic field result is still the best evidence we have for the existence of an ocean on Europa. Jupiter's moon Callisto. It is the outermost of the Galilean moons. Callisto orbits Jupiter at a distance of about 1,168,000 miles. It takes the moon about 7 Earth days to make one complete orbit of the planet. It is also experiencing fewer tidal influences than the other Galilean moons because it orbits beyond Jupiter's main radiation belt. Callisto is tidally locked, so the same side always faces Jupiter. At 3,000 miles in diameter, Callisto is roughly the same size as Mercury. It is the third largest moon in the solar system, after Ganymede and Titan. The mean surface temperature of Callisto is minus 218.47 degrees Fahrenheit. The average density of Callisto at 1.83 grams per cubic centimeter suggests a composition of approximately equal parts of rocky material and water ice, with some additional volatile ices such as ammonia. Ice is believed to constitute 49 to 55% of the Moon, with rock component likely made up of chondrites, silicates, and iron oxide. Beneath the surface is an icy lithosphere that is between 80 to 150 meters thick. A salty ocean 50 to 200 kilometers deep is believed to exist beneath this, thanks to the presence of radioactive elements and the possible existence of ammonia. Compared to the other Galilean moons, Callisto's surface is quite dark, with a surface albedo of about 20%. An immediately obvious feature about Callisto's surface is the ancient and heavily cratered nature of it. In fact, the surface is the most cratered in the solar system and is almost entirely saturated by craters, with newer ones having formed over older ones. Callisto has a very tenuous atmosphere composed of carbon dioxide, which has an estimated surface pressure of 0.75 micropascals and a particle density of 4 times 10 to the power of 8 per cubic centimeter. Because such a thin atmosphere would be lost in only about 4 days, it must be constantly replenished, possibly by slow sublimation of carbon dioxide ice from Callisto's icy crust. While it has not been directly detected, it is believed that molecular oxygen exists in concentrations 10 to 100 times greater than carbon dioxide. This is evidenced by the high electron density of the planet's ionosphere, which cannot be explained by the photoionization of carbon dioxide alone. However, condensed oxygen has been detected on the surface of Callisto, trapped within its icy crust. Those are the four big moons of Jupiter, but it still has dozens of other moons since Jupiter's tides are 100 of times stronger than Earth's. The next biggest moon after the Big Four is way smaller, named Amalthea. It's an irregular lump about 250 kilometers across its longest dimension and is red, probably polluted by sulfur from Io. It orbits just over 100 kilometers from Jupiter's cloud tops. The moons get smaller and more irregularly shaped from there, with Himalaya and Thebe and Illara and Pasiphae, down to Hegemony, Kale, and Kalicore, which are no bigger than hills. Many of the irregular distant moons of Jupiter orbit the planet backwards relative to the others, in what are called retrograde orbits. They may be captured asteroids from the nearby asteroid belt. Many of the moons have orbital characteristics that are very similar to, which may indicate that they were once a single object that broke up. Several such families of moons orbit Jupiter. 9 spacecraft have studied Jupiter up close. Pioneer 10 was the first spacecraft to fly past Jupiter. It was then followed by Pioneer 11, Voyager 1, and Voyager 2 flybys. NASA's Juno spacecraft is currently studying the gas giant planet from orbit. In fact, NASA's 2011 Juno mission to Jupiter is named after her because the Juno spacecraft paves through the clouds of Jupiter's upper atmosphere to reveal its secrets. In Greek mythology, Juno peered through the clouds to reveal her husband's muses, aka Jupiter in Roman mythology. The spacecraft, which arrived at Jupiter in July 2016, is the first to study the planet's mysterious cloud shrouded interior. Thank you so much for listening. This will be the end of my report. My name again is EJ, telling you to always stay curious. Remember, there's a whole wide universe for you to explore. Goodbye.